Okay, let's start with flash sintering. We talked about different sintering techniques, conventional, non-conventional. Those are, well, I wouldn't say non-conventional, but those that utilize the applied external pressure or applied external field like SPS. Today we're going to talk about flash sintering, which is related to SPS, related to the so-called um, electrically assisted sintering technique. So for flash sintering, researchers can apply current, typically DC current, directly through the sample for sintering without application of pressure. But later on, people are getting, as what we are going to show, getting more towards applying some pressure. Okay, but in the first embodiment of the flash sintering, people do not apply pressure. This is the schematic of um, the, I guess, the earliest experiment for flash sintering. Of course, you have computer control, and you have a so-called dog bone shaped sample. Dog bone shaped sample. You see this one? Yes. And then it's hung in through so-called a platinum wire. A metal wire goes into the inside of the furnace. Of course, you can apply a DC power supply to apply current through the sample. And this whole setup is placed in a typically box furnace or a tube furnace. And then you can use mechanism to observe it, CCD camera to observe what is going on. Of course, you can also optically measure the temperature. Okay, so again, this part is sample. You put that in the furnace, you apply electrical current. You see these two holes is actually where the platinum wire will go through the sample. And of course, when they did that, they applied some platinum paste to assist with the conduction of the electricity through the wire into the ceramic piece. Of course, in this case, it needs the ceramic piece to at least have certain conductivity. In the earlier, one of the earlier experiments they did was a yttrium stabilized zirconia, also called YSZ, has certain conductivity and are ionic conductor. And the feature is that the current directly goes through the sample, which is related, not exact to SPS. In SPS, sometimes the current can go through the surrounding so-called die, because you are using a graphite die. Here, when Dr. Raj's group did it, there's no conducting die around it. The current just passes directly through this dog bone shaped sample. So, okay, current directly goes through the sample, and the advantages, of course, we can in principle achieve extremely fast heating. We're talking about hundreds of degrees C per second, really fast heating within a few seconds, and in some cases. And in principle, if everything was done quickly enough, we can preserve the fine microstructure, which is beneficial for certain mechanical applications. Okay, of course, there are always disadvantages. Not a very clear mechanism, at least for different material. People are still debating them. We have some understanding, but not complete clear of the mechanism. And the limited sample choice and sample geometry dimension. For example, dog bone shaped sample. Once you have this dog bone shaped sample, where can you use this dog bone shaped sample? Very limited use, if at all. And dimension, you can imagine it's difficult to do this over a large sample size. Okay. But anyway, flash sintering is getting a attraction. Here we are showing the mechanism of observed linear shrinkage versus the furnace temperature. In this case, you are applying a different so-called electrical field, voltage per length. In this case, you are applying different electrical field. Let's say through the so-called dog bone shaped sample between the two poles, right? Because the platinum is essentially highly conductive. You don't lose much voltage over there. Pretty much all your voltage loss is between your ceramic material. Make sense? And then you have 0 volt, which means you do not apply any electrical field. And then you increase to 20 volt per centimeter, 40, 60, 75, all the way to 120 volt per centimeter. Imagine that dog bone shaped sample. Essentially, between the two holes, you are applying 120 volt, okay, DC voltage. And then they apply this voltage, and then at the same time, they are heating the furnace. Remember, they hung the sample in a tube furnace or a box furnace, initially at room temperature, and then they read this. Constant heating rate. This is constant heating rate is not by the electricity through the sample, but you apply the voltage. Initially, the resistance is too high. There's almost no current. Makes sense? Because it's insulator, almost an insulator. But as you gradually ramp up the furnace, which means the furnace gets heated up, and at the same time, your small dog bone shaped sample also heats up at a rate of roughly 10 degrees C per minute. A slow heating, a typical slow heating. You're heating the furnace, at the same time heating the sample, and meanwhile you are maintaining this your 0 voltage, and you observe, let's say optically, observe the shrinkage. You observe the shrinkage because the length you can observe using a microscope on the side. Make sense? You can observe it. And then at different temperature, essentially at different time, the sample initially when the temperature is low, there's no shrinkage. Initially from 700 to 900, no shrinkage. But let's say you have 0 volt. You did not apply any electrical field, but gradually by and by 1100, 1200, and then the sample starts to shrink, right? That's your typical pressureless sintering. Also, 0 volt means without electrical field, without current. Make sense? But at the same time, if you do this similar experiment at 20, this circle, you see that, okay, now you have an electrical field, and initially no shrinkage, but by and by at around 1100, it starts to bend down, means it starts to shrink as the temperature goes slightly higher, and it accelerates compared with this one, compared with the 0 volt. Make sense? And then, of course, you can keep ramping up the voltage. Now the square is for 40 volt per centimeter. That's your electrical field. And then still you do this experiment. You gradually heat up your furnace. Okay, initially no shrinkage, and then at similarly around 1100 it starts to bend down, which means it starts to shrink. But it shrinks even faster. Remember here the temperature 1200 does not mean your sample temperature. It just means your environment, the furnace temperature. Remember, in this case, Dr. Raj's group is heating up the entire furnace. And when the electrical field, the current goes through the sample itself would also heat up. That provides the additional heat to the sample that makes this sintering goes faster or slower. Faster, right? Faster. Or at the same ambient temperature, much larger shrinkage. Make sense? And of course, they continued at 60 volt. You see, initially no shrinkage, but then up to 1000, it starts to drop down instantaneously. You see, it's 10 degrees C per minute. From here to here, roughly 10 degrees C. Within a minute, the shrinkage is done. Make sense? and he kept increasing up to, let's say, 100. The onset temperature drops. You see the so-called onset, or the so-called inflection point, a sudden change in slope. Make sense? A sudden change in slope. Onset, so-called flash sintering, gets lower and lower. You see at this 120, it drops down to 800 some 50-ish. At 120 volt, as long as he heats up slowly his furnace to 850, maintain the voltage suddenly. Within seconds, the sample achieved almost full densification or did all the shrinkage. Make sense? So that's what Dr. Ross observed. Extremely fast sintering. Within minutes or even within seconds. And the ambient temperature is still low, but the sample temperature can be extremely high. In a way, we see, okay, this offers the potential for so-called energy saving, because I don't have to heat up the whole thing and wait for this long. Make sense? Because your whole furnace body is a lot of mass to heat up. Okay? Here is a related plot also by Dr. Rush's group. Similar result. We are plotting shrinkage strain versus temperature, and then 0 volt, different. He's probably trying two different electrical field. One is 0 volt, one is 100 volt per centimeter. That's electrical field strength. Okay, and then he's still doing this constant ramp rate of his furnace at 10 degrees C per minute. And this 1 micron, 2 micron, 5 micron, 10 micron, what do those mean? Those are grain size, his starting particle size. Make sense? And naturally, 0 volt, which means no electrical field, the finer the starting grain size, the so-called faster sintering or densification. Make sense? 1 micron, when the furnace reached 1400, it has the most shrinkage. While 10 micron, you have very little because you have very little driving force. We'll talk about that in a second. Make sense? The smaller particle gives you driving force, at least from this 1 to 10 micron range. Okay, let's pause. Yeah. One question is whether the constant heating rate is necessary for flash sintering. No, it is not. For example, if a related experiment that Dr. Raj's group did is maintain the furnace at 900, for example, and step up gradually the electrical field, right? I heat the thing up, the furnace as well as my sample, to 900 instead of all the way to 1500. I just hold it here. 0 volt, I have no sintering, but then as you step up the voltage or the electrical field, suddenly the flash sintering would happen. So in that case, they achieve the same thing. Okay, so when for the second set experiment, 0 volt versus 100 volt, different particle size, we see, okay, of course, finer particles sinter so-called quicker, densify earlier. But then, even for flash sintering, the finer particles would have a lower bending or onset temperature, inflection point or onset flash sintering temperature. Make sense? Okay, because you have larger driving force. So this is another plot that I borrowed from Dr. Rishi Raj. We are plotting the time for sintering to achieve, let's say, densification versus the so-called temperature, but again, not sample temperature, the ambient or furnace temperature. Okay, and we have different so-called sintering regime. Conventional sintering, let's say we are using yttrium stabilized zirconia or YC. Conventional sintering, you have to heat up your furnace all the way to 1400 degrees C, and you have to hold for roughly this long. 10,000 here, the unit is second. 10,000 seconds is 3 hours, right? Here is 30 hours. So roughly, when you heat up to 1400 degrees C or somewhere in here, you are talking about roughly 3 hours of sintering time. Little bit longer, little bit shorter, but you have a range. That's your window. Okay? And then this is conventional sintering, which means pressureless. No pressure, you just heat up the sample, let it happen. Of course, you can do so-called HP or hot pressing, which means during the sintering, you at the same time you apply some external pressure. And here, with that help, of course, you can decrease your external or ambient temperature from 1400 roughly to 1200. And your sintering time decreased from 3 hours roughly to, well, 1 hour, something like that, or even shorter. Make sense? Because your energy, your driving force not only now come from thermal, now also come from mechanical. And further, people talk about SPS, spark plasma sintering, or F fast field, electrical field assisted sintering, T4 technique, fast field assisted sintering technique, which encompass SPS. Now we are talking about we can further reduce the so-called surrounding environment temperature from 1200 each to 1000, 1100. And the time we are talking about, well, 300 seconds, which is 5 minutes or somewhat longer. You see what I mean? And then finally, flash sintering. We are talking about ambient temperature, the surrounding temperature is 800, 900. And the sintering time, we are talking about, wow, 3 seconds, 10 seconds. So you see, these are different so-called sintering paradigm or regime, different technique. And of course, in terms of instrument simplicity, this one is simplest. But probably this one is, in terms of energy efficiency, this is probably pretty low. This one is probably pretty high. But in terms of control, when the sintering is not like all advantage, because if sintering happens too fast, there are also other tricky stuff that would happen. For example, thermal expansion. You may have, because everything expands too quickly and shrink too quickly, you may develop so-called micro cracks within the material, which is not what you want sometimes. So it's not all advantage, not like everything you wanted to be here. But at least from energy point of view, conceptually, when you move down this curve, we can, in principle, save energy, save time, make the productivity higher. Okay? But at the same time, some people start to challenge, is flash sintering merely a thermal runaway? Because we are passing current through the sample. Is that just the uncontrolled jaw heating? We all know jaw heating. When current passes through a conductive sample, the sample heats up. We call that jaw heating. And a flash sintering is just the thermal runaway, which means not very well controlled jaw heating. Well, there have been some studies, and some people kind of start to feel that is at least the part of the mechanism. I wouldn't say complete, but at least a part of that mechanism. Different group, very famous professor. This is in United Kingdom. Dr. Chen is from University of Pennsylvania. At least they are different from Dr. Raj's group, but they kind of have a feeling that it's probably related just the jaw heating effect. Okay. And what happens for these types of YZ types of material is that their conductivity increases with increasing temperature. Think again. conductivity increases with increasing temperature, which means the hotter the sample gets, the sample becomes more conductive. And then under a constant voltage, remember what you learned in high school physics. The voltage square divided by your resistance is your power. The lower your resistance, the higher the temperature, the lower your resistance, your power goes higher. And the higher the power, you heat up even more and your resistance drops even lower. So from that sense, it kind of makes sense, right? It's so-called self-accelerated sintering. Make sense? Yeah. For these type of sample, the higher the temperature, the lower the resistivity, the higher the conductivity. But the higher the conductivity means the smaller the resistance through the sample. And then from what we learned in high school physics, U square divided by R. Because quite often people do this under so-called constant, initially at least, voltage mode. Remember what we showed Dr. Raj's group, 100 volt per centimeter. He was applying a constant voltage. So in that sense, constant voltage square divided by resistance. Of course, you have higher and higher power, the higher the temperature, and it becomes so-called self-accelerating. Okay?